Hello everyone, and welcome to the Distribution Plots lecture for Seaborn. In this lecture, we're going to discuss different plot types with Seaborn that allow us to visualize the distribution of a dataset. Let's go ahead and jump to the Jupyter Notebook to get started. Okay, here I am at the notebook. I'm going to get started by importing Seaborn, and by convention we import Seaborn as SNS. And since I'm in the notebook, I'm going to go ahead and say matplotlib inline. That way I can see our visualizations inside of the notebook. Alright, now let's get some data to plot. Seaborn actually comes in with a few built-in data sets that you can directly load. And I'm going to grab one called tips and save it as a data frame called tips. You can do this by just saying tips is equal to SNS load dataset and then pass in tips as a string. And this will load the tips dataset. And then I can actually check the head of the tips data frame, and it looks something like this. There's 7 columns here, and this is basically just data referring to people who had a meal and then left a tip afterwards. So you have the total price or bill of the meal, how much they left as a tip, the gender or sex of the person leaving the tip, whether or not they were a smoker, what day and time they ate their meal at, and then the size of the party. Alright, let's go ahead and discuss our first plot type, which is dist plot. DIST plot. The dist plot allows us to show the distribution of a univariate set of observations. And univariate is just a different way of saying just one variable. Let's go ahead and explore this. I'm going to say sns.distplot. And then for a dist plot, what you do is you just pass in a single column of your data frame. In this case, let's go ahead and see how the total bill is distributed. So I'm going to say total bill and then run this cell. And you should get a plot that looks like this. If you get a warning here, don't worry about it. That actually has to do with another package called stats models. It won't affect your actual Seaborn code. But here we don't have any warning, so we're okay. Notice here that I get basically a histogram and what's known as a KDE, a kernel density estimation. That's this line here. Later on in this lecture, we're going to discuss what this KDE is and how we can actually build it up. But for now, we can remove it if we want to by saying, as an additional argument here, KDE equals false. And just by typing KDE equals false, now you essentially just have a histogram. And a histogram is essentially just a distribution of where your total bill lies. So you can see here that on the y-axis you have a count, and then you have these bars on the x-axis as bins. And this basically means that most of your total bills are somewhere between $10 and $20. And if you want to get a little more information out of this, you can change the number of bins. So you can go ahead and as a third argument, say bins, and then set an appropriate number of bins. And this number really depends on your data set, but let's go ahead and choose 30 for now. And now we can get a little more, basically, definition. And we can still see that most of the bills happen between 10 and 20. If you choose a bin value that's too high, for instance, let's go ahead and put in 100, you'll start to get kind of a weird scenario where you're essentially beginning to plot every single instance of total bills for every single price point. So you usually want to try to find a balanced bin size, but that really depends on your plot itself. Okay, looks like we have a good idea of the information here. And if we can read this graph, we can basically just say most of the bills happen somewhere between $10 and $20 and begin to fade away as you get higher and higher in bill price. That's the dist plot, and that allows you to visualize a distribution, essentially a histogram. And you can add a KDE plot on top of that, but we'll learn about KDE plots later on. Let's talk about joint plot. And joint plot from Seaborn, we can say SNS joint plot, allows you to basically match up two dist plots for bivariate data, meaning you can essentially combine two different distribution plots. And bivariate is just two variables. And we also have a kind parameter that we're going to play around with, which allows us to choose how we actually want to compare these two distributions. Let me go ahead and show you how we can use sns.jointplot. First, you have to pass in an x variable, and then you have to pass in a y variable, and then you have to pass in your data set. Let's start from the back end. So we'll pass in our data set as tips. So that's our data frame. And then for x and y, you just pass in strings that are column names, the two things you want to compare to each other. So for instance, maybe I want to compare the distribution of the total bill versus the tip size. Let's go ahead and do that. I'm going to say total bill as my x, and on my y-axis, I'm going to put in tip, the tip column. So right now, I'm just passing in the total bill column, the tip column, and then the data equals tips. And I get a plot that looks like this, which is essentially just two distribution plots. Here we can see the tip on the y-axis and total bill along the x-axis. I'm going to zoom out so we can see the whole plot. And then in between, I have a scatter plot. And the scatter plot actually basically makes sense because it looks like it has a trend that as you go higher in total bill, you will go higher in tip. And that makes sense because tips are usually proportionate to your total bill. Now, joint plots actually give you an additional argument parameter called kind. And this kind parameter allows you to affect what's actually going on inside of this joint plot. Right now, by default, it's scatter, but you can also pass in an argument such as hex. And hex allows you to make basically a hexagon distribution representation. It's similar to scatter, except basically if the hexagon has a certain number of points in it, it gets darker. And if it has less points, it gets lighter. Essentially, it's just a way of not having to put all those scatter points on, but instead showing a distribution with these hexagons. Another argument we can put in for kind is reg, which stands for regression. And this will look a lot like a scatter plot, except seaborn is actually going to draw a regression line on it. Now, we haven't actually learned about linear regression yet as far as a machine learning topic, but later on when we do approach that topic, we'll come back to this and actually discuss how this line is built. But essentially, this is just showing almost like a linear fit to the scattered point data. And you can actually see it has a p-value and a Pearson coefficient, which we'll discuss later on when we actually discuss linear regression. Finally, another kind that you can put in here is KDE, and that allows you to have this two-dimensional KDE, which essentially just shows you the density of where these points match up the most. All right, let's go ahead and move on from joint plot. We'll usually be using joint plot with the default scatter, because that's the one that's essentially easiest to read and gives you quite a bit of information right off the bat. We're going to go ahead and expand that idea by showing you pair plot. And pair plot is essentially going to plot pairwise relationships across an entire data frame, at least for the numerical columns. And it also supports a color hue argument for categorical columns, which I'll show you later on. But we see here on top that we have this joint plot. What pair plot is essentially going to do is do this joint plot for every single possible combination of the numerical columns in this data frame. Let me go ahead and show you what I mean. Because it's going to do it for all the combinations, basically you just have to call sns.pairplot and pass in your data frame. And this is something we're going to be doing quite a bit throughout the course. Keep in mind, the larger your data frame, the longer pair plot takes. So a lot of times pair plot takes a while if you have a very large data frame. This data frame is relatively small, so we're okay. And note here, we basically have a pair plot for all the numerical column values. So we have size versus total bill, size versus tip, and then when you get to a parameter versus itself, for instance, size versus size, instead of actually doing a scatter plot, which wouldn't make sense since you just have a straight line, you see a histogram instead. And same thing for tip versus tip, and for total bill versus total bill. That means pair plot is a really nice way to quickly visualize your data. And what's even nicer is that you can add a hue argument to this. HUE. And the hue argument is where you would pass in the column name of a categorical column. And categorical means not numerical or continuous, but actual categories. For instance, the sex column is categorical because there's two categories in it. There's male and female. And when you pass this in as hue, you pass in the column name, hue equals sex, and it will color the data points based off of the column you put in for hue. So here, all the green points are female based on this legend, and all the male points, we're going to zoom out so we can see the whole thing, all the blue points are male. And as a third argument, you can specify a palette. And the palette allows you to actually color this with some specific color palette. We're going to discuss palettes and color and style at the very end of the Seaborn lecture series, but right now I'll just show you an example. Essentially, there's these color map strings that are from matplotlib that you can pass in as palette, and they will choose certain colors for whatever the parameters are. And here we can see now male is blue and female is this kind of light pink color. All right, we'll touch in on palettes and colors and styles a lot more. Let's go ahead and move on to rug plots. And rug plots are actually a very simple concept, but we're going to use the concept of a rug plot to actually build and explain what the KDE plots we saw earlier were. I'm going to go ahead and say SNS rug plot, and just like dist plot, the distribution plot, you're going to pass in a single column here. So we're going to say tips, and let's go ahead and pass in the total bill column. And what the rug plot does is it's a very simple concept. It just draws a dash mark for every point on this uniform or univariate distribution, essentially one single variable. So instead of like a histogram, let me go ahead and make that dist plot one more time to compare. I will say SNS dist plot, tips total bill, run that, and let's go ahead and say KDE is false. Okay, so the difference between a histogram here below and this rug plot is that the histogram essentially has bins and it counts how many dashes were in that bin and then shows it as a number up here. And that means there's between like 10 and, 11, there's about, if we take a look at this, 45 dashes there. And they're all kind of stacked on top of each other. And then over here, as we go further in total bill price, there's less rug or less dashes, and that means the bin is going to be less high. That's the basic relationship between this histogram and this rug plot. Again, rug plot, really simple concept. You just draw a dash mark for every single point along the distribution line. All right, that's the total bill. What we want to do is build off of this idea of rug plots to explain what this actual KDE plot is. And that's going to be this line right here. How do we actually build this line based off of these rug plots? And you can see that it kind of has a relationship to the rug plot count. KDE plots stand for kernel density estimation plots. And you can actually Google this and check out the Wikipedia on kernel density estimation plots. And the page will look something like this, kernel density estimation. And this is a really, if you scroll down, this is a really nice figure right here. And this is essentially what we're going to try to construct. You'll notice that each of these black dashes here is the rug plot, so the actual points, and then you have these little normal Gaussian distributions on top of each point, and then you sum them all up to get this final kernel density estimation. Now, what do I mean by normal distribution or Gaussian distribution? Well, if you also look up on Wikipedia, that's just in probability theory, the normal distribution, and it's probably the most common continuous probability distribution. Essentially, it's these kind of normal distributions where you say like, oh, how did everyone do on their test? And you grade all the students and then see the distribution of scores. It's usually something normalized like this, or for instance, people's ages or people's heights. Usually a lot of things tend to follow a normal distribution. Okay, let's go ahead and jump back to the Jupyter Notebook and touch upon these topics in a little more detail. In order to do this, I'm going to copy and paste some code from the notebook, and you don't need to worry about understanding this code. It's just to build out a diagram for explanation. I'm going to go ahead and copy and paste this. I've copied and pasted this code, and let me break down real quick what this code's doing. I just have a few imports. I create a data set of random data, then I use a rug plot on that random data. I set up the x-axis for the plot, use NP linspace to create 100 equally spaced points from xmin to xmax. And then here, this is probably the hardest part to understand because it uses a library we haven't talked about yet, stats.norm. All this does is it plots a normal distribution for each of the rug plot points. And that looks like this. If we go ahead and zoom in on this, here I have my data set, and this is a random data set, so if you run this, yours may look a little different. But keep in mind, we're not working with tips anymore. We're just working with some random data. Notice I have blue dashes here, and then these gray lines represent normal distributions on top of each of these blue dashes. So this is a normal distribution centered around this dash. And we have a bunch of them on top of each other. What we're going to go ahead and do next is sum them all up to get the kernel density basis function. And this is just the sum of all of these little normal distributions. Alright, copying and pasting the second block of code from the notebook allows us to actually sum up all these basis functions, which are just these normal distributions. Once you sum them all up, you get something that looks like this, which is just the KDE plot from before. And that's how the KDE plot is constructed from the dist plot, the very first plot we looked at, dist plot. Alright, so those are all the major ways you can show distributions of data with seaborn. Let's go ahead and quickly review all the various plot types. The distribution plot types, if we scroll back up, they were the dist plot. And again, the dist plot, you can use it with two methods, have KDE equals false and essentially just see a histogram, or leave this blank, and then you can actually see the KDE, the kernel density estimation, which we kind of explain at the end. It's just the sum of all the normal distributions around a rug plot. Joint plot is really similar to this idea, except you're passing in two columns, and you pass them in as x and y arguments, with your third argument equal to the data. Then the next plot we learned about was the pair plot, and the pair plot is just building off of the joint plot, and essentially is a joint plot for every single column or numerical column in your data set. And that means you just pass in the data set itself, that data frame. And you can pass in the hue and palette if you want to actually color by a categorical column. Next plot we learned about was rug plot. You usually won't be using rug plots, but it's there for you. And the main idea of using a rug plot is to kind of build the logic of the kernel density estimation plot, which is done through this code here. You can take the time and read through this code, but I just wanted to get the point across that when you're using a rug plot and you want to build a kernel density estimation plot off of that, the KDE plot, you can do that just by saying rug plot, pass all these normal distributions onto each point, and then take the sum of all those points, and that's the kernel density estimation plot. And we've seen how we can do that using dist plot. And as a quick point, if you are using dist plot, here, we know that we can get rid of the KDE plot by saying KDE equals false. If you actually just want the KDE plot and don't want the actual bins here, you can actually pass in, instead of dist plot, you can do SNS KDE plot, and then pass in tips, total bill, and this will build the KDE plot without any distribution of the bars. All right. Hopefully you realize that seaborn is incredibly powerful and also very simple as far as the code you need to write. Everything we did was just done in one line. If you try to do this in matplotlib, it would have taken you multiple lines. But what's nice about this is that it works off of what you know of matplotlib. And we'll see that a lot more when we talk about styling and colors. A lot of that matplotlib knowledge is going to be transferable to actually editing little things in this plot. Okay. I hope you're beginning to enjoy seaborn. Again, like I mentioned before, it's one of my favorite libraries, and I can't wait to show you the next couple of plot types we're going to learn about with seaborn. Thanks everyone, and I'll see you at the next lecture.